A person stands at the base of a loose, shifting slope and looks up, weighing whether it's even worth trying. They've got a backpack, water, and the constant awareness that one poorly placed step could force a retreat or a call for help. It's not about fitness or courage. It's that the ground moves under every footfall, and no wheeled vehicle can keep steady traction there. That's where an idea appears, almost primitive yet radically new. A horse that doesn't tire, doesn't spook, and adjusts every step with mechanical precision. That idea has a name: Kawasaki CORLEO, a rideable quadruped robot designed to turn rugged mountains into passable terrain. The key detail isn't that it can walk. It's that it can maintain true dynamic balance under the weight of a person, across unpredictable surfaces, without losing stability when the ground gives way. Today, when terrain turns technical, personal mobility narrows to two options: go on foot, with all the strain and risk that entails, or rely on infrastructure built for wheels. Enduro motorcycles and 4x4s improve traction, but they still depend on continuous, relatively uniform contact. In deep gravel or on stepped rock, wheels spin or hang suspended. A legged system, by contrast, can choose discrete footholds, the way an animal searches for solid purchase in a specific crack. That's the gap CORLEO aims to close, not rolling over terrain, but negotiating with it, step by step. This isn't fantasy. In 2023, engineers at Kawasaki Heavy Industries publicly unveiled a concept for a rideable quadruped robot, with posture and geometry inspired by a horse. Each limb integrated electric actuators, and a control system worked to maintain stability while the upper body compensated for movement. It wasn't a commercial product or an immediate promise, but it was a clear technical statement of intent. Merge advanced locomotion robotics with human rider ergonomics. The core challenge is physical. When a human mounts a four-legged system, the total center of mass rises and shifts with every movement. Each step demands calculations of force, angle, and timing in fractions of a second. If one leg lands on a loose rock, the system must redistribute load to the other three before the tilt exceeds a stable threshold. Power alone isn't enough. It requires constant terrain perception, sensors measuring inclination, pressure, and acceleration, and algorithms that adjust joint stiffness like virtual muscles. That's where the idea becomes more ambitious than just an alternative vehicle. This isn't about softer suspension or more aggressive tires. It's about building a machine that can feel the ground and alter its gait in real time, absorbing impacts and keeping the upper platform relatively stable so the rider doesn't have to fight every jolt. If that works outside a lab, in real mountain conditions, the line between walking and driving would start to blur, and climbing would stop being exclusively human, becoming a new form of personal mobility. The technical challenge doesn't begin with power. It begins with control. A quadruped like CORLEO has to decide where to place each foot before the body even reaches that point. To do that, it combines inertial sensors that measure acceleration and rotation, position sensors in every joint, and potentially vision or environmental mapping to anticipate irregularities. The system builds an internal model of the terrain and calculates foothold trajectories that keep the support polygon beneath the combined center of mass at all times, even when the rider shifts their weight forward on a steep climb. Robotics has already proven that this kind of dynamic balance is possible without a rider. In 2020, the Boston Dynamics Lab demonstrated how its quadruped robot Spot could move across stairs, debris, and inclined surfaces while maintaining stability after external disturbances. That validated that predictive control algorithms and the coordination of multiple degrees of freedom could operate beyond perfectly flat environments. But placing a person on top changes the equation. The system has to filter oscillations, limit vibration, and maintain a posture comfortable enough for extended travel. To achieve that, each leg functions as a chain of electric actuators with high-precision gear reductions that allow micro-adjustments of torque. They don't just lift and lower the limb, they modulate stiffness, as if tuning the tension of an artificial tendon. When a mechanical foot detects that the surface gives slightly, the controller reduces vertical force and increases lateral stability. If it finds solid rock, it can apply more thrust to push the body upward. All of this happens in milliseconds, with control cycles recalculating the system's state dozens or even hundreds of times per second. There's also a crucial ergonomic dimension. A real horse partially decouples the vertical motion of its back thanks to the natural elasticity of its muscles and spine. In a robot, that elasticity has to be engineered. CORLEO integrates a central structure that acts as a stable platform, partially isolated from extreme leg vibrations through absorption systems and active control. The goal isn't to eliminate movement altogether, but to keep it within predictable limits so the user can lean, adjust posture, and actively participate in balance without feeling like they're riding an unstable machine. Control can also incorporate the rider's intent. Sensors in the handlebars or saddle can detect shifts in weight or pressure and interpret them as commands for direction or speed. It's not a simple throttle, it's continuous interaction, where human and algorithm share responsibility. If the rider leans left on a slope, the system doesn't just turn. It adapts the step sequence to prevent the downhill side from losing support. The bottleneck is energy. An electric quadruped carrying a person requires high energy density batteries and efficient thermal management systems. Every step consumes power not just to move forward, but to stabilize. On long inclines and uneven terrain, consumption rises sharply. That forces a trade-off between range, weight, and power. More battery means more mass to lift with every stride. Less battery limits real-world mountain range. If that balance between control, ergonomics, and energy can be achieved, the result wouldn't just be an exotic vehicle. It would mark a new category of mobility, one capable of moving where wheels simply stop making sense. But that promise depends on every one of those subsystems working together under dust. Cold, shifting inclines, and inevitable human error. Only then would a mechanical animal stop being an impressive demo and become a reliable tool in the real world. Now imagine it in actual use. A rescuer needs to reach an AIHT person in an area no conventional vehicle can access, where every minute spent walking drains energy that will later be needed for evacuation. A rideable quadruped could move across fractured rock, step over small drops, and maintain stability while the operator conserves strength. It wouldn't eliminate effort, but it would reduce the constant friction of fighting the terrain. In mountain exploration, remote infrastructure inspection, or even controlled adventure tourism, the experience wouldn't feel like driving. You'd sense a rhythmic sway, subtle adjustments beneath your feet, an immediate response when you shift your weight. It wouldn't be silent or ethereal. You'd hear electric motors working and feel that every incline demands real energy. Clear limits would emerge as well. In deep mud or unstable snow, the legs could sink more than expected. On extremely smooth surfaces, the lack of grip would force a reduction in speed. And range would shape every decision. Planning routes around available charge, factoring in recharge points or swappable batteries. Safety would demand sensor redundancies and controlled shutdown systems in case something fails, because a sudden loss of balance on a slope is no small matter, even if the system is designed to minimize that risk. In terms of availability, CORLEO was introduced as a concept in 2023, and it does not yet exist as a commercial product available to the public. If development follows the usual pace of advanced robotics and certification testing, a limited version for professional applications could emerge sometime between 2032 and 2035. For broad recreational use with clear regulations and stable production, a more realistic horizon shifts to around 2038. The initial cost would be high. Comparing it to current industrial quadruped robots and specialized electric vehicles, a first rideable generation could land around $250,000. In a scenario with optimized production and denser, more affordable batteries, that price could fall to roughly $80,000. Reaching that level would require significantly higher production volumes, a lower cost per kilowatt-hour of battery capacity, and simplified high-torque actuators. What ultimately matters isn't just whether it can climb a technical slope in a controlled demonstration. It's whether, after hours of use, it still maintains precision, sufficient range, and the kind of reliability that makes someone choose it instead of walking. If that happens, the line between trail and road will no longer be defined by wheels or by human footprints. And the real question won't be how far you can go on foot, but which parts of the physical world remain truly unreachable when your vehicle can take a confident step of its own. A rideable quadruped robot aims to transform mountain mobility by replacing wheels with dynamic legged balance. This is the engineering challenge behind turning a mechanical animal into a real-world tool.